Welcome to another example video. So let's jump right into it. Here you are told that your ideal operational amplifier has infinite voltage gain and infinite slew rate. So this is asking you to state what is meant by voltage gain and slew rate. All right, so we're going to start with voltage gain first. Voltage gain, normally symbol that we will use is G, is the ratio of V out to V in. So we'll write that down. This will be the ratio of voltage output to voltage input. The term voltage is very important because we talk about voltage, not current. So if you just say input over output, you will lose mark. All right. And the next one, infinite slew rate, or like what I like to call no lag. Okay. So infinite slew rate here, it means that if there's no lag, right, when you change your V in, this V in, your V out will respond immediately. There's no lag. When you press something on your keyboard, immediately the letter will come out. There's no lag. When I change the pen color, immediately the color will change. Won't change halfway as I'm writing. No lag. Okay, so I will say that the changes in V in the input voltage or voltage input voltage results in immediate changes to output voltage. So if you use an app or if you use Discord, right, there's this thing called the ping. Okay, so they call this the ping because the faster the time in between the ping, then the less lag it is. What infinite slew rate means no time lag at all, zero. The ping is 0 millisecond. Okay, so that's the idea of the op-amp. Pretty normal stuff. We're going to move on. So sometimes you have to identify the circuit, but in this case you don't have to because this is a non-inverting amplifier. All right. So how do you know it's non-inverting? The most telling sign is your V plus not grounded. Okay. V plus not grounded, meh? No, you see this V plus? V in is equal to V plus because this part is connected to your non-inverting input. And then you might be thinking, oh, miss, where is V minus? V minus is in the middle here, lor. Okay, so your V plus is your V in. Your V minus is in between the junction between two resistors. So if you can identify the potential divider circuit, that is better. This is actually a potential divider circuit that we bend into half. So all these feedback loops are all just sneaky potential dividers trying to hide. How sneaky? Okay, so I'm just going to change color a bit halfway. All right, so this one is your potential divider circuit. The pink color side is your feedback loop. This one here. So we also have the supply. Just keep the supply in mind because normally people will ignore the supply. So I'm going to circle it so I remember. And then whatever that comes out of this end will be the output. So here is actually V out. Okay. All right, pretty standard stuff. It's non-inverting because the V plus is not grounded. Okay, ground is here. Whenever we see a circuit, immediately you should get through the common points in your brain. This is 0 volt. So this is 0 volt. You know we are going to straighten this one already. Somewhere along the line. But let us read the question first. Okay. Supply to the op-amp is plus minus 9 volt. How nice. They gave us the voltage gain. The voltage gain of the amplifier circuit is 12. Interesting. So for a voltage gain of 12, you are asked to determine the resistance of resistor R. So basically find R. The gain is 12. So gain is 12. There are two ways to do this. Either you already know the equation for gain, which is 1 plus Rf over Rin. Okay, this will be equal to 12, or Rf over R1. So when you use this equation, you have to be careful. What do you ratio? The resistor here is the feedback resistor, the one on top. The slew rate of my computer, as you can tell, is not infinite. Hello? Give me a... Okay, we're back. So the RF is the feedback loop. So if we scroll back to this one, this RF is this pink color one. Okay, the feedback loop. And the Rin will be the remaining one, 1.5. So I would take R divided by 1.5. Why is the equation like this? All this will be in the theory video. Okay, so I will take R divided by 1.5 kilo ohm times 10 to the power of 3. There. So you can see the slew rate is not infinite at all. All right, so from here, we're going to move on. And hopefully the computer holds up. Ding ding, to find the value of R. So R will be 11 times 1.5 E3. Okay, so this is 16.5 kilo ohm, or basically what I found this one, it would be 16500 ohm. Okay, 16500 ohm. 16500. Okay, so because this one here is ohm, so you either put I will put 16.5 kilo lah. So I'll put 16.5 times 10 to the power of 3. All right. Okay, so this is your resistance. But if let's say you be like, Miss, I don't remember the equation. Can I use potential dividers? Sure. Okay, so we'll straighten this wire. Here, you will have your resistor R, which we are trying to find. And somewhere underneath here would be the 1.5 kilo ohm. Hashtag pray for my computer. This part is grounded. Okay. All right, so this one is 0 volt. Okay. So if this is 0 volt, then this one is also VOUT. Right? But you see, this part here is V in, because V plus is equal to V minus, right? So we're going to put here, this is V minus, yes, here, but it's also equal to V plus, and it's also equal to our V in. So let me highlight. This one is negative, this one is positive, this one is the same. So what was the idea again? We said that if you don't want to saturate, V plus and V minus have to be equal. If not, then it's a comparator circuit. If these two is equal, when I put V plus as V in, V plus is V in, and V plus and V minus must be the same to prevent saturation. So V minus is also V in. Whoops, V minus is also V in. Ding ding. Okay. So now we're going to write out the potential divider equation. I will write it down here, so I got space. So I will say that the potential divider from the potential difference from here to here, okay, which is V out minus V in, over the resistor R. Okay, again, apologize for the faulty graphic card, but like that lah, that is life. Got the soldier on. If not, your videos won't come out, then we GG now. Alright, so continue. This side will have V in minus 0, the green color side. V in minus 0. 1.5K. Okay, so this one I can keep as 1.5 for a nicer number, but this is 1.5 kilo lah. Just FYI. Alright, so now what we can do is we can actually find the ratio of G. because our G is the ratio of V out over V in. So our purpose here is we want to find the ratio of V out over V in. So we gotta just start cross multiplying and doing all the mathematical magic. All right, so we're going to cross multiply. You will have 1.5 V out. See the slew rate. Minus 1.5 V in is equal to R times V in. Come on. Okay, there we go. All right, so what do we do? What do we do? We got to do a gathering. 1.5 V out is equal to R times V in plus 1.5 V in. So I will factorize V in, okay? V in here will be R plus 1.5. And this one will just be 1.5 V out. So I'm looking for the ratio between V in to V out. So I will take V out over V in. All right. And I bring this one over lah. This is R over 1.5. So divide bring the 1.5 over here to divide. Plus 1.5 over 1.5. And this one happens to be, what is this again? Brain hang a bit. This one happens to be 1. So I can now say V out over V in is R over 1.5 plus 1. And this is the one that we will use. Ding, 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 ding. Ding, ding. Let me draw a box around this. So from here, gain is equal to R over 1.5 plus 1. So if you look at this carefully, you will notice that the R is the feedback resistor. So this one is actually our RF. I'm going to write here for you. This is RF. Okay, and down here is the other resistor that is connected to the input. This is R in. So you get gain as RF over R in plus 1. And this one is equal to, what's the gain again? The gain is 12. 12. Well, 1.5 plus 1. So you will be able to find R. Okay. So in this case, you will get the same value, 16.5, but this is kilo ohm. So this method is a fail-safe for you. Okay, we use potential divider to arrive here. But you don't need to if you can remember this relationship. There. Gain is 1 over RF over R in. Sorry, 1 plus RF over R in. That will be the gain. All right. So what is important here is either you memorize the equation, but they can ask you to prove the equation at any time. So the skill has to be at hand. Memorizing this will allow you to save some time. Okay, moving on. For this circuit, the variation with time t of V in is drawn. So this is our V in. Is this, ooh, so interesting. Is this triangle wave? Very nice. Okay. On figure 9.3, show the variation with time t, the output potential. Okay, so this is your input. And you are asked to show the output. How would the output look like? All right. So if you want to find the output, right, what you can do is to think about the gain. Gain here means multiply. So our gain in this question given is 12. All right. The gain given is 12. So multiply the entire thing by 12. So the easiest thing to think about is 0. 0 times 12 is 0. Lor. So this one will be 0. Okay. This is corresponding to this point. I'm going to just, I guess, label the points and hopefully it won't crash. I apologize for the lag, but there's nothing much I can do about it at this point. So here, this one would be your maximum, which is 1. 1 times 1 times 12 is 12. So this point will become 12, which is here. So we just sketch out the entire graph, multiply by 12. And because of the lag, I can't seem to plot corner plots. Why are you like this? Why? Okay, there we go. So I complain about it. So this part here will be a straight line. I'm gonna just draw a straight line. Okay. I guess something like this. You draw a straight line, or you draw it as straight as you can. Okay. So what happens at the bottom triangle? This is the same, right? Bottom triangle here. This is negative 1. Negative 1 times 12 is negative 12, because this is non-inverting. So you don't have to change positive to negative. Okay, so hang on. Now this one is negative 12, so it's here. And obviously at T2, it will drop to 0 lah. Okay, so you're going to get a straight line that also looks like this. Bloop, parallel lor. This kind of graph come out very nice one because it's 4 marks. All right, so if you stop here, you don't get full mark because are you forgetting something? Are you forgetting something? Does the op-amp have the ability to give you 16 volt? Sorry, not 16 volt, 12 volt. The power supply can give you 12. Miss, you didn't label 12. Oh, yeah, lor. The computer lag, I also cannot see clearly. Life is hard for a boomer to teach online, you see, guys. Okay, so now, okay, wait, I should keep the color for the people who are confused. Okay, so this one is this point. I'm gonna connect. Sorry about that. Cut off train of thought, but this is better. So this one is 12. VOUT is 12 here, and down there, VOUT is negative 12. But can the supply give you 12? Go back and stare at the circuit and see. Oh no, only 9, not 12. So we need to snip. We need to cut off the wave at 9. So what you do is during the exam, you draw this straight line. And then by the time you reach 9 is, okay, I'm going to zoom in a bit. Don't lag. Okay, so 9 is here. This is your saturation current. So your wave will be here. 999999999. So basically, if you learn German, it's a bit like no. So this part, you will have to draw a dotted line because it's not true. It's not true. It's fake news, guys. They say they want to multiply us by 12. Q set music. I don't have editor. They say they want to multiply this one by 12. But actually, the highest they can give me is just 9. So when the input is 1, you cannot get 12. The largest you can get is 9. So that means if you actually draw this in a straight line, okay, this intersection point here, ding. Okay, a bit out, hang on. This intersection point here, I mean, this line is obviously not straight, but if you draw it in a straight line, it should be here. Okay, where it chops off. And then if you go back up, this is 1, 2, 3 cm. 1, 2, 3 cm. It will correspond to here. 1, 2, 3, 4. Nope. Correspond to, wow, my eyes. Correspond to here. Let's say I call this TS for saturation, not TS Elliott. So this TS for saturation is actually 1/4. Okay, the saturation time is 1/4. My line is not straight so it looks a bit weird, but ideally your graph should look like this. It's gonna chop off at this point. Okay, chop at this point. All right, so there's always a way to test, because when you take the halfway mark here and then you ... you will notice that this happens to be 0.75. That is the maximum gain that maximum V in that you can have before your op-amp saturate. So another way to test whether it's 0.5 is by calculation. You can say that the gain is 12. So during saturation, the VOUT is equal to 9 volt. So 9 over V in is equal to 12. From here, you can see that V in will be 0.75 volt. 9 over 12 become 3 over 4 lor. So V in is 0.75. This is your saturation input. Okay, so if your V in is 0.75, this is where we saturate. Okay, this is the saturation value. So this is how you can tell lor. Your TS is 15 small boxes or 3 cm. The reading is 0.75. You take 0.75 and the 9 volt saturation, the supply voltage, and you divide. You should get the same gain, which is 12. So basically, we are chopping off at 9 here. This TS is here. Okay, hopefully that makes sense. All right, so here is where we chop. Okay, I'm back. Anyway, as I mentioned just now, stop lagging. Just stop, computer. You can do this. It's just a graph. All right, so here, this is your TS, saturation point. Okay, so this is how you can check. All right, when you double check your saturation point, let's say you chop it off here, your input should be 0.75 at this time, which is 3 cm. I don't know what TS is, they didn't give me the scale, right? So at this 3 cm, the input should be 0.75, so that 9 divided by 0.75 will still maintain a gain of 12. Okay, or you can just draw the actual wave and then you snip at 9. Okay, so here is the same thing. Again, my graph is not perfect because this is not a straight line. Let me make this a straighter line. Ta-da! The line is straight. Okay, let's continue. So we're gonna chop it at 9. Okay, so but this time is -9. So if you look at this graph, -9 is somewhere beneath this one. Okay, can you? Is my pen working? Nope, my pen is not working. Okay, as I was saying, this one is -9 volt. The struggle is real. So you check, here is where we cut. Okay, where is -9. This point is where we cut. So we will draw a straight line here. 9. So we cut off the short part. All right, then if you want to, you can take out an eraser and change this into dotted lines. You don't want to draw dotted line also, never mind. But I find that having this is useful for you to double check your answer. So once again, this TS is at the symmetrical, right? So 5 boxes away from T1. So 5 boxes away from T1 is here. So when you ding, 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 this one, the V in is 0.75 volt. Okay, so here is when saturation happens. So whenever you draw this kind of graph, you have to be mindful about 2 things. Number 1, the saturation happen. And if saturation happen, where is it saturated? Is it at 9 volt? Is it at 5 volt? Because this will actually affect your graph. Okay, so you must know where to cut. And in this case, we are cutting at 9 because the supply is 9. Okay, so I guess if you want to, I can label here for you. This point here, the op-amp saturates here, this point here, and also all these values. Okay, op-amp saturate now. Snip. All right. So second thing you have to be aware of is this an inverting or a non-inverting? If it's an inverting, everything that is positive must draw at the negative. Everything that is negative must flip over to draw at the positive. So I write here lah. Number one, you look at gain. Number two, you must check your saturation point. Have you saturated? Check the supply voltage. And number three, you should think about, is it inverting? I think the inverting or non-inverting one should be number one. Sorry, I changed my mind. Tick, tick. Okay, so first thing you ask yourself, what type of circuit? Inverting? Non-inverting? Because whether it's inverting or non-inverting, your gain will be positive or negative G, depending on whether it's inverting or non-inverting. So then you draw your graph lor. You multiply the graph, it will be bigger. Okay, this one doesn't look bigger because they mess up a bit lah. They use the different scale. But on the same scale, you actually will see the differences is quite large. Because if I try to draw V in on this one, V in is just 0 to 1 volt. 1 volt is kind of small leh. Okay, let me try to draw V in first. Okay, I have drawn the V in for you. 0, okay, I zoom out a bit. 0 to 1. Multiply by 12 should get the black triangle times 12. But supply will chop it by half. So you go through this step. Is it inverting or non-inverting? Since it is non-inverting, the polarity will not flip. Okay, so it's non-inverting, polarity will not flip. The gain is 12, so 1. This one is 1, it will become 12. But doesn't reach 12 because the saturation is 9. So you grow until you reach 9, you stop, flatten. Grow until you reach 9, stop, flatten. So there's some part of the signal cannot already. So let me show you a bit of the something that is similar when you, let's say you do sound recording. I'll show you. Ooh, look at this. There's infinite mislead. Okay, now I want you to look at this mic aux thing here, this one down here. Okay, now currently I'm speaking at a certain level where it is not saturated. Okay, so you can see, oh, I talk very loud. I do physics as ASMR. Alright, so this one will fluctuate. But what if my voice is very loud or I create a very loud sound? Okay, like I tap the mic. So look at the entire bar turning red. Hello, I think it just self-adjusted. There we go. So it can... Last one. So whenever it turn red, it means that there's some op-amp inside the voice driver that is connected to the computer that has turned red, saturated level. So you can't really hear when I'm speaking soft and when I'm speaking loud because just snip. Okay, so that's all for this one. So lots of operational amplifier in your life. If you're wondering where the mark is, if you show a straight line from 0, 0 to the gain to 9 volt, this straight line is 1 mark. You draw a horizontal line like this is the second mark. Okay, the saturation point will change from positive to negative 9 volt. At T1 is 1 mark, and then this line is 1 mark. So essentially, what they are telling you is, boys and girls, I'm very happy to give you 1 mark for each portion of the correctly drawn graph. 1, 1, 1, 1. All right. So if you find this interesting and you want to try one similar question, my suggestion is to give Winter 13 paper 43 a try. You can see the op-amp saturate now. See, the one that come out already. Winter 13 paper 43 a good try. The shape of the wave is the same. It's like that triangle sawtooth wave, but don't take it for granted. They can give you any kind of shape they want. All right. So in the next example, I won't go through the potential divider method again. I will just jump by straight using into the equation. Hopefully here you understand how to draw the graph and you get a greater appreciation to what it means by the op amp being saturated. Okay, so that was a bit of behind of the scene for the recording there. So give these questions a try. If you find this video helpful in your study of operational amplifier, do give it a heart shape, give it a like, whether you're watching it on stream or YouTube, and share it with your friend so that we can learn physics together. Subscribe. I will see you in the next example. Go try this question. Go. Bye bye.